We started with numericals type 4 and we have solved one numerical which involved gate cathode characteristics, and I had given one more numerical as an homework. So we'll solve this today now. I hope that at least some of you have tried solving this at home. So I'll not be drawing the gate characteristics and the gate circuit, but we will simply incorporate all these equations 1, 2, 3, 4. Okay. So given gate participation is 10 milliwatts is equal to 0.01 watt. Eg equal to 10 volt. Given slope equal to m equal to 3000. Okay, and Rg is to be found out. Okay, so from the gate cathode characteristics passing through origin, we have Vg equal to 3000 times Ig. Okay, Pg is equal to Vg into Ig is equal to 0.01 watt, which is equal to 3000 times Ig into Ig is equal to 0.01. So Ig is equal to under root of 0.01 upon 3000 is equal to 1.826 milliamperes. Okay, from the gate circuit we have Eg equal to Vg plus IgRg, which is equal to 3000 times Ig plus Ig into Rg, which is equal to Ig into Rg plus 3000. So 10 equal to 1.83 milliamperes to Rg plus 3000. Okay, this comes out to be 2.464 equal to 2464 ohms. Okay, yeah, so we have one more interesting numerical here. This is having some different details. I'll tell you how to solve it. An SCR has VGIG given as Vg equal to 1.5 plus 8 times Ig. In a certain application, the gate voltage consists of rectangular pulses with 12-volt amplitude, 50 microseconds duration, and duty cycle equal to 0.2. Find the value of Rg in the gate circuit to limit the peak gate power dissipation to 5 watt. Okay, so this is as before, only thing is that Vg equal to 1.5 plus 8 Ig. Second important thing which is different compared to the previous two numericals is gate voltage consists of rectangular pulses with 12 volt amplitude, 50 microseconds duration, and duty cycle equal to 0.2. Okay, and we are supposed to find the value of Rg in the gate circuit to limit the gate power dissipation to 5 watt. Okay, so in this numerical, the gate voltage or the trigger voltage is not directly given as 10 volt, or it is not given as 15 volt as in the previous two numericals, but it is given that the gate voltage is not DC, it's not a pure DC voltage, but it is having the form of rectangular pulses with 12 volt amplitude, 50 microseconds duration, and duty cycle equal to 0.2. Let us try to extract some meaning out of these things. So what is given here is this thing. So we can say Pg max equal to 5 watt. Second thing given is Vg equal to 1.5 plus 8 Ig, and Eg is rectangular pulses (12 volt), duty cycle equal to 0.2, and duration is equal to 50 microseconds. So this is my Eg, and Eg is of this type. So amplitude is 12 volt, (50 microseconds), and duty cycle. So if I say this is T on, okay, so it is given duty cycle equal to 0.2. So you know that duty cycle is equal to T on upon T. Okay, so we know that this is T on, this is T off, and the combination of both is equal to T. Okay, so duty cycle is equal to T on upon T equal to 0.2, and you know that the T on is given as 50 microseconds. Okay, so T equal to T on upon 0.2, Okay, so yeah, now students understand that this waveform, okay, so the waveform which starts at this point and ends at this point, this kind of a waveform is applied to the gate circuit. Okay, so this is applied to the gate circuit. Okay, so gate participation is given as 5 watt, given Pg is equal to Vg into Ig equal to 5 watt. Okay, now this is the average gate participation. This is the average gate participation. So also Vg is equal to 1.5 plus 8 Ig. Therefore 5 equal to 1.5 plus 8 Ig into Ig, which is equal to 1.5 times Ig plus 8 Ig square. So this becomes a quadratic equation, 8 Ig square plus 1.5 Ig minus 5 equal to 0. So we can use the formula for solving it. Therefore Ig is minus B so here A equal to 8, B equal to 1.5, C equal to minus 5, minus 1.5 plus or minus so it becomes 1.5 square plus 8 into 4 into 5, 162.25 on 16, so it's equal to minus 1.5 plus or minus 12.74, 16. So we have minus 1.5 plus 12.74 on 16, So we know that gate current cannot be negative, so we have to accept this value. So we can say, therefore Ig equal to 0.703 amperes. Now we also know that Eg is Vg plus IgRg, which is equal to yeah. So this particular trigger voltage Eg is having a rectangular nature, and if we speak about peak participation, then we have to consider the value equal to 12. Okay, so now since Vg is 1.5 plus 8 times Ig, which is equal to 1.5 plus 8 into 0.703, which is equal to 7.124 volts. Okay, so now the challenge is, what is the value of Eg? Okay, students, understand one thing here, that in case of a rectangular waveform, the average value is always equal to duty cycle into the amplitude. Okay, so we use this thing. So pulse amplitude is this thing. This is the pulse amplitude. So in our case, we can write EG AVG is delta into 12 equal to 0.2 into 12 is equal to 2.4 volts. Okay, but see, calculating the average content is not going to help. You know why? Because if I write down EG AVG here, then it is 2.4 minus 7.124 upon 0.703. This will not work because this will give value of RG as negative. That is why we cannot do these things here. Okay, why? Because if average power was given, then we have to make a different kind of a calculation, but it is given peak. Okay, so peak gate power dissipation. Okay, so when the amplitude is present as 12 volts, that is where when it is peak. So we have to write down here So now we have the fifth type of numericals which are asked. It is numericals involving safety factor. Okay, fine. Calculate the PIV rating of a thyristor connected in three-phase 6-pulse bridge inverter having an input voltage of 415 volts given voltage safety factor equal to 2.1. Okay, so the important statistics which is present in this is input voltage is 415 volts and the given safety factor is equal to 2.1. There is a straightforward formula here for PIV, and what is unknown is the PIV rating. Okay, so using the PIV is equal to root 2 into V in into the safety factor. Okay, so the safety factor is abbreviated as SF. Okay, so which is equal to root 2. V in is given as 415 and safety factor is 2.1, which comes out to be 1232.5 is equal to 1232.5 volts. Okay, so the answer is another numerical of this type. Compute the safety factor for thyristors used in three-phase 6-pulse converter connected to 415 volt mains given PIV is equal to 1500 volts. Solution: given PIV is 1500 volts, V in is 450 volts, safety factor is unknown. Okay. Okay, so we have solved 3 numericals today. 2 numericals on type 4 and we have solved 1 numerical on type 5. So this relationship is important. Fine. Draw all important waveforms associated with the operation of the circuit shown below. Okay, so draw all important waveforms associated with the operation of the circuit below. Okay, circuit is as follows. Haril? Fine. So can anybody guess what is the technical name which can be given to this circuit in front of us? Okay, so what is the technical name of this circuit? Yeah, can anybody tell what is the technical name which can be given to this circuit? Okay, I will give you some hints. First, it is watt energy to watt energy converter. Yeah, what do you think this circuit converts energy, electrical energy, from which form to another? Yes, what do you think does this circuit convert electrical energy from which form to another? What should I write here? This is input. This is output. Yes. What is this?
It is half controlled rectifier.
Okay. So why did you say it is half controlled?
Only one diode.
Okay, so one diode is there, so there will be control over only one half cycle. Okay, can you tell me which cycle is controlled and which is not controlled?
Positive cycle is.
No, you are wrong. Positive half cycle is not controlled. Negative half cycle is controlled. Can you tell me why you are wrong and why I am right? Hmm? So you told an answer that sir, positive half cycle is controlled and negative half cycle is not controlled. Yeah. Why did I say that your answer is wrong? What is the meaning of the word control? Hmm? When we say that we have to control infection, that means what? When you say that you have to control infection, that means what? You should stop infection or you should allow infection? Yes, this is a very simple question. When I say control the infection, that means do you have to stop the infection or allow the infection?
Stop.
Stop the infection, right? Now in this circuit, which half cycle of the input is stopped from being sent to the load?
Negative.
Negative half cycle. Yes, that is why I say if you stretch the definition of infection, then here at the input there is both positive and negative half cycle. Do you agree? In the input side there is positive
Yes,
as
sir.
well as negative half cycle. What do you get at the output?
Only
What do we
positive.
get? Positive, right?
Only
So
positive.
negative half cycle is not going. That is why we say negative half cycle is controlled. So because I am stopping the negative half cycle from being sent from the source to the load. That is why I say negative half cycle is controlled. On the other hand, if I reverse the direction of the diode and I make this diode connected like this, now can you tell me which cycle will not be sent?
Positive.
Yes. So now in this case, I can say that negative will be sent, positive will not be sent. So when you reverse the direction of diode, you say that negative or positive cycle has been controlled. So that is what. So we need to have proper understanding. Okay. So now what I'm doing is that I'm connecting an SCR instead of a diode. So now tell me, this will lead to a rectifier. So now this is a rectifier or a converter? Now this circuit is a rectifier or a converter? Yes, this circuit now has a diode, so it is a rectifier or a converter. What is the difference I said between a converter and rectifier? Does anybody remember? Yes? You remember I said there is something called as controlled rectifier and uncontrolled rectifier. Yes, now say. Yes?
Convert one form of energy into another.
Pardon? Repeat, I could not hear. There is a break in audio.
Convert one form of energy into another form.
No, I am not asking that question. I am asking that when you use a diode between load and AC supply, that circuit is called as converter or a rectifier.
Rectified.
Rectifier. So rectifier means uncontrolled rectifier. So now this is a rectifier or a converter? This is a rectifier. It's an uncontrolled rectifier. Is it okay? So if you use a diode between an AC supply and load, then that is called as uncontrolled rectifier or a plain rectifier. But if I replace this diode with an SCR, and if I fire this SCR at omega t equal to alpha, then the same circuit now becomes a controlled rectifier or a converter. Okay. Now whether this is half wave or a full wave. Now this SCR, when it is put between the AC supply and the load, will it be able to control both half cycles or only one of the half cycles?
Only one half cycle.
Only one. Which half cycle it will control? Positive or negative?
Negative.
No, it is both. You know why? Because as I told you that in this single phase AC supply, the maximum voltage available at from the input is 325 volt. Okay, and 325 volt is less than the breakover voltage of SCR. So this single phase supply will not be able to fire the SCR in absence of gate drive. Okay, so in absence of gate drive, the SCR will continue to remain in the off state because the maximum voltage which occurs at the input side is at omega t equal to pi by 2 radian, and the value of voltage is 325 volts, which is less than 600 volts breakover voltage VBO. So I must apply a firing pulse here. So now till the firing pulse is not applied, SCR will not conduct. SCR will not conduct. There will be an open circuit between VS and RL. That means in this particular circuit, to say that only negative half cycle is being controlled is wrong. Answer is both half cycles are controlled, in the sense negative half cycle is completely blocked because negative half cycle at input will reverse bias the SCR, and SCR is a unidirectional device. It can conduct, if at all, only if it is forward bias. I repeat, SCR can conduct, if at all, only when it is forward biased. That means there is a possibility of SCR conducting only during positive half cycle, and in that positive half cycle also, till the firing pulse is not applied, SCR will not conduct. That means from omega t equal to 0 to 2 pi, there will be two kinds of controls. From pi to 2 pi, negative half cycle is completely blocked. That is full control of negative half cycle. And from omega t equal to 0 to omega t equal to alpha, also positive half cycle is controlled. So although we say that this is a half controlled converter, still I can say from basic definition, this circuit is able to control some portion of positive half cycle and also the complete portion of negative half cycle. Okay, so technical name here, because there is only one device, so we said is half wave. Okay, so the answers are input obviously is AC energy and output is DC energy, but then it is not pure DC, it is impure DC. So at the input we have pure AC and at the output we have both impure DC and also impure AC. And if it is an impure DC means it is a pulsating DC, and pulsating DC can be converted into pure DC by using suitably designed filters. Okay, that we have already studied in our yesteryears. Okay, so here the input Vs is a combination of positive half cycle and negative half cycle. Now, positive half cycle forward bias is the SCR and negative half cycle reverse bias is the SCR. Okay, positive half cycle exists from 0 to pi and negative half cycle exists from pi to 2 pi. So SCR can conduct between omega t 0 to pi, and because in the negative half cycle it is reverse bias, it cannot conduct between pi to 2 pi. Now in this 0 to pi, we understand that SCR will not conduct till it is fired at omega t equal to alpha. Therefore, we can say SCR will not conduct between omega t equal to 0 to alpha. So we can say the conduction periods in this circuit, or we can say conduction intervals, are omega t greater than equal to alpha less than equal to pi, and non-conduction or blocking intervals are of two. First non-conduction interval is omega t greater than equal to 0 less than equal to alpha, and second non-conduction or blocking interval is omega t greater than equal to pi less than equal to 2 pi. Okay, so the entire negative half cycle will be blocking. Yeah, the further discussion will be taking in the next lecture.